is Stucchio. I'm the head of data at Simple. We're a pay later engine, um, and so basically, I'm going to give a somewhat much more on the ground talk, useful for day-to-day people who open up Python and crunch data every day. So here's a question for the audience. How many of you are happy with your data set? Does it answer every question you want answered? Does it work for you? Could it be a lot better? Who's really happy with it? Yeah, I didn't expect to see very many hands on that. So I've gone through many stages of grief. I've tried constantly to get my data better. And eventually I just sort of approached the idea that I'm going to accept that my data is bad. And I'm going to see what I can do in spite of that. So this talk is not about improving your data. Your labels are wrong. A lot of stuff is missing. And it's going to stay that way. If you can fix things at the pipeline stage, you absolutely should do that. But in most cases, you can't, due very frequently to things beyond your control. So this talk is about taking that into account and drawing correct inferences anyway. It is a bit pessimistic, but at the same time, I do consider it realistic. So the recipe I want to get across in this talk is, instead of treating your data as a reflection of current reality, and instead of treating it as something you want to use to predict the future all by itself, instead treat your data as a reflection, as an imperfect picture of what's actually out there in the world. So I'll sort of talk about the present and the future. And so normally speaking, the way I see most people working, myself included as often as I can, is I'll do some data cleaning, but apart from that, I'll assume my data is correct. Let's say I get a credit score from a vendor. I'll assume that credit score is true. And I'll train a predictive model, hope for the best, and if the rocket you see is good enough, I'll push it to production. What I want to convey in this talk is there's another approach which you often have to get to, is you get unfixably dirty data. Let's say 10% of your data is just missing for some reason or another, or it's just wrong somehow. What I want to suggest here is, instead of treating your data as your input, treat your data as the product of a random process. Build a model for how your data went from reality to whatever's in your data frame. Then you build a model to predict current reality from your data, and then use the outputs of this model, which are a better reflection of the world outside your system, as the inputs to your final model, which is trying to predict the future. So most of this talk will be going through examples of this in a little bit of detail. You should treat this sort of as a recipe you can follow yourself. None of these are going to be things you can directly apply to your problems, but the ideas will hopefully suggest a way to work. So missing data is a common problem. And here's a situation I found myself in. So I was building a product that was doing what is essentially a funnel analysis. So we have a whole bunch of visitors that land on a website. We ultimately want to take them to checkout, and we want to know the intermediate steps. How many will add a product to a cart? How many will click the purchase button? How many will actually enter their credit card? And how many will finally click the purchase button? And it's called a funnel analysis because these diagrams, if you were to draw them the other way, looks kind of like a funnel as it gets narrower approaching the bottom. So I started looking at my data, just diving into what was available. It was actually quite difficult to get this data. There was more than a month of delay because I was first told, SSH into this server and you can access it. The server was actually running at 100% CPU and 100% disk. It turns out to be the production server. So then I asked them could I just get access to the backups? Why are you giving me access to production? They're like, backups? Can't you just SSH in and do it there? So I'm like, do you mind if I take down production? Which obviously led to about a month. And a month later, I got actual backups. So this is ultimately the data that came out, oversimplified. And so it looks pretty straightforward. I have visitor ABC. He entered his credit card at 12 and he purchased at 1. I have visitor DEF entered his credit card but decided not to purchase. And then I have visitor JKL who never entered his credit card but somehow managed to purchase. I mean, I would love to be able to do this on Amazon. So let me remind you why it took me a month to get this data. There was a production server running at 100% everything. There were no backups. So just going in, I kind of felt like maybe engineering best practices weren't being followed with this system. So I inquired a little bit about the architecture. So there's a JavaScript tracking pixel, which tracks all these events, sends them to a single production server, which is collecting quite a lot of data per second. Um, for some reason, it's being put into hundreds of SQLite databases. So there are easily hundreds of databases running per disk, which for those of you who know how disks work, let's say it's a spinning disk, a spinning piece of metal, and each time you want to write to a different place, it needs to spin, write, spin somewhere else. This is really not an optimal way to go. Traditional database will have one per disk at most, and it'll spin, write a big chunk, and essentially try to minimize disk seeks. But if you have two databases running on the same disk, none of that works. So I was just thinking, is it possible that this data collection system itself is the reason for this? Is it possible that this system that I didn't write and have no control over maybe is losing some data? So at this point, what I want to do is I want to construct a probabilistic model of data loss. So let's reiterate our recipe. A naive way to do this would be just take the data I have, and I want to calculate a conversion rate, which would be the fraction of people who make a purchase. So I take the purchase time, and if it's null, I'll call that a false. And if it's not null, I'll call that a true. So that's when a purchase happens. And then I now have a Boolean value, which is either true or false. I take its mean, and I will get the fraction of trues. This is Pandas code. I'm sure it's slightly different in R, but that's the basic idea. And that'll get me kind of an estimate of the conversion rate. The idea I want to describe is I want to identify latent hidden variables, which in this case are basically going to be what actually happened in reality. How many people actually made a purchase, how many people actually entered their credit card, and additionally, what fraction of data points is this server losing, just due to all the odd things about its design. And then the final model, it's a very simple model. It's just measuring a conversion rate. But the point is what's going into this is a statistical estimate of the number of purchases made as opposed to just the count of purchases made by this tracking pixel. So what we want to do is we want to model the generating process. So the probability of a visitor entering the credit card is some number, which we don't necessarily know, but that's one of the things we want to find out. The probability of a purchase conditional on a user entering a credit card is another thing we want to know. We also don't know it, but these are the goals of the system. We also want to know the probability that an event will be observed given that it occurred. So if a person enters their credit card, what are the odds this will be reported to us? And as we kind of inferred from before, that number is significantly less than 1. So the first two, the blue ones, are interesting to customers, and the red is interesting to us because that's sort of telling us what's the gap between what we built and what this system needs to be. So here's some data reported to us, summarized. We had 1 lakh unique visits, 40,000 cases with a credit card entered but no purchase, another 10,000 with a credit card entered and a purchase, and 5,000 with no credit card entered but still a purchase. So what we want to do is we want to back out what actually happened here. So this is a probabilistic model that comes more or less from basic arithmetic. The fraction that entered the credit card is red because we don't know it, but it's binomially distributed. There's 1 lakh visitors, so that's the end of the binomial distribution. And the probability is this unknown parameter, the fraction who are going to enter their credit card. The number we observed is, again, a binomially distributed variable coming from the number who entered their credit card, which is unknown, and the observation probability, which is also unknown. So in the second line, the 40K is what we know, what's literally in our data, and everything on the right side is unknown. And then as you work your way down, this is basically ordinary probability theory, just with a whole bunch of unknown variables that we want to find out. So what we want to do from this is we want to actually find out the conversion rate. So this is a probabilistic model. It's based on some assumptions we're making about how the world works, and more importantly, how the data comes to us. So PyMC is a great library when you have some complex probabilistic model and you want to come up with estimates from it. This is, if you notice, this code is almost just this. You write down your probabilistic model. Since it will typically be done in the Bayesian method, you need to come up with some priors. So for instance, for the conversion rates, I'm taking a uniform prior. All conversion rates are equally likely. Sorry, not equal, equally likely. And then the rest of it is just describing our mathematical model in terms of both the things we know and the things we don't. So PyMC is great. You can write down models this way, press solve, it'll do Markov chain Monte Carlo, and it will give you probabilistic estimates. And so the end result of this is, if you do PyMC fully, it'll actually give you a range. I'm just reporting the midpoints. So with this implicit statistical model, even though the conversion rate we can observe directly just by counting is 15%, the actual conversion rate is 16.7%, which is 11% higher than 15%. And this comes from basically inferring that our rate of data loss is 10%. And that means that we're actually having 10% more conversions approximately than are reflected in the data. So this is the key implicit modeling assumption. We enter a credit card. Before you submit, it is impossible to skip this step. So if this is false, the whole thing breaks down. But given this relationship in where our data comes from, the rest of it falls out from simple probability. So this is not going to be as simple as just feed all your data into a deep neural network or into gradient boosting and expect something good to come out. You really have to think about all the processes happening in the middle. The key point is the data which is present does give clues about what is missing. And once you can come up with a better estimate of what's missing, you can draw useful conclusions. Here's another problem that happens quite frequently. Data is just wrongly labeled. Formats are just different across different sources, and you have to bring a whole bunch of sources into one. So here's a problem I face that's simple. This is my phone. It's a fancy Google Pixel. I'm mostly in Bangalore, sometimes with the in-laws in Hyderabad. And so typically speaking, Simple should kind of expect my purchases to be in these locations. They should expect my purchases to be happening on this kind of a phone. Suddenly, Simple gets a valid request to make a purchase from this device, whatever the heck it is, some weird-looking Nokia thing, in Jaipur. I went to Jaipur once. It was pretty. Probably won't go back. Does this seem right? Is it possible that maybe it's not actually me, it's someone else who would like to make a purchase on my account? Most likely. And so probably this transaction should be stopped. Someone should call the actual registered phone number, confirm the purchase. Have you given your OTP to anyone on WhatsApp? Because we don't use WhatsApp. Ask some probing questions of that nature. So, brilliant plan. If devices don't match the historically used devices, let's flag it as potential fraud, escalate to the fraud calling team, don't let the purchase happen, call the customer up, check if they've shared the password, check if they've given out one-time passwords, that kind of thing. So then I looked up my own data. This is my device history across several different Simple merchants. And As you can see, that capital Google, capital Pixel 2 XL is not equal to the other thing. There's also a version with a plus, which is some kind of URL encoding. There's all sorts of funny variations that happen like this. And basically what's happened here is that these are all coming from different merchants who've implemented our system. These merchants haven't all implemented it the same way. There might be other steps of the pipeline somewhere in between the merchant and me that also change this stuff. So there's a lot of people involved in this process. There's the merchant partners, and there's the business development team that's usually the one communicating with the merchants. There's a product manager somewhere in the way who helps integrate merchants with Simple. There's the engineering team. Engineering team actually does this almost perfectly. So getting this fixed would be a team effort. I don't really believe that teamwork makes the dream work. Our merchants, you can go outside to our booth and see who they are. Mostly they don't care that much about stopping a smallish number of fraudulent purchases on our platform. A fraudulent purchase on their platform is still a purchase. They get paid, we're out the money. Our biz dev team really wants to close the next big sale. Like, it's very reasonable for this not to be their top priority. So getting something like this fixed is not going to happen quickly and quite likely may never happen. And I'm just going to accept that. Instead, I'm going to try to solve this problem with linear algebra, which I actually enjoy a lot more than trying to wrangle up a whole bunch of people to finally feed me good data. So, sorry. This is my phone. This is reality. The strings I have in my data are a reflection of it, but they are not actually reality. So I'm going to model things this way. The data is something that comes from reality, but is an imperfect reflection of it. My data set is, of course, going to be exactly what you see here. It'll be my user ID. There is a specific partner merchant where the device is being used. There is the reported manufacturer, the model. And this is a function of my data, but this is a function of reality, but is not true reality. So, since I like to solve problems with linear algebra, I've actually been doing this since the NumArray days, which Peter and a couple of others might remember. I'm going to set up a matrix. So my columns are going to be reported device strings. So each column and a row will be a user. So that first row means that particular user showed up with that Google Pixel XL2 capitalized as you see on merchant A. They did not show up with an iPhone X on A. On merchant B, they showed up with a Google Pixel 2, the word XL missing. On merchant C, they never showed up. And also on merchant B, they did not show up with an iPhone 10. And similarly, the second guy didn't show up on merchant B. He did show up on C. So those are all reports. And that last row, there's something a little funny. This person showed up with a Pixel XL2 on A and an iPhone on A. So this matrix is highly incomplete. Most users don't use most merchants. So it's a matrix completion problem. And we have to basically sort of infer what the NANs are in the matrix. The other observation we can make is that this matrix is low rank. There are a lot of strings. Each device generates a lot of different device strings. But the rank of this matrix should essentially be the number of devices that are actually out there in the world. So even though so essentially, if we go back to this matrix, the Google Pixel shows up as a 1 in 3 different columns in this oversimplified matrix. So 10110 is what generates the Pixel. 01001 is what generates the iPhone. And these are the things that should essentially be repeated. So the rank of this matrix, so this matrix is essentially 2 different linearly independent vectors repeated a bunch of times. So the rank of this matrix actually should be the number of devices, not the number of device strings, which is much larger. So we have a matrix completion problem, and it's very low rank. If this seems familiar, those of you who work in recommendation engines may have seen it, because that's how a lot of recommendation engines work. So can we use that to deal with our data problems? Basically take techniques from recommendations and solve this. And the answer is yes, we can. So we know our matrix should look like this low rank approximation. So we have our user vector, tensor product our device vector, and that essentially represents all the people who are using the same device. And then there's an error term, which will come from basically those weird fraud cases or a person who uses two phones. And those should be uncommon. So as I said, this is kind of like a topic model. The tensor products are our topics. And the error term, which in our case are attacks, are directly analogous to, if we think about topics, let's say a person's major topic is violent action movies, but also for some reason he likes the movie Notting Hill. Just one weird one-off case that doesn't say he's in general interested in romantic comedies. He's generally violent action movie guy, but also he just likes that one movie for some idiosyncratic reason. And then the user is a document, and an attacker is a document that fits into multiple topics. So remember, this matrix is very much non-square. There's a lot more users than there are devices. So what we can do is, if we want to get a nice symmetric matrix, we can just compute m adjoint m. And if we do some simple arithmetic on the ijth component here, we discover this is the number of users who were seen having device I and also device j simultaneously. And as per our model before, this is not strictly true. This is stylistically true. There's a bit more arithmetic that I'm suppressing because I don't want to make this take too long. But essentially, this matrix can be thought of as a bunch of topics which have size n. N is roughly the number of people with a given device. So there's a lot of people out there with a Pixel. There's a lot of people with the iPhone. And then there's error terms which are on the order of size 1. Which will basically be how many people use a Pixel and also a strange little Nokia thing. How many people use an iPhone 10 and also a Huawei S2600. The number of people who simultaneously use two phones will be much smaller than the number of people who strictly use one. So what this means is that, and by the way, in this, what I've done here is I've taken all the NANs and I've filled them in with zeros. So what this means is that I should have a set of symmetric matrices, and that dj, tensor product dj, that has eigenvector dj by definition, and it's of size n. I also have a bunch of weird one-off terms that I'm not interested in, which are basically going to have like a 1 or a 2 there. So I can take this matrix and I can threshold it. I can basically find some cutoff between the typical number of people who have a given device and anything below that, I'm just going to set to 0. So if I do that, then what I can do is I can just find the eigenvectors of m adjoint m, and after the thresholding, these vectors are going to be the right singular vectors of m, and therefore, essentially, it's going to be a bunch of ones, or actually, it's not going to be ones, but it'll be non-zero entries in certain places. The non-zero entries mean that this device corresponds to these things, and everything else is unrelated. So essentially, each DJ is going to be 0, non-zero, non-zero, 0, a bunch of zeros, some more non-zeros, and all the non-zeros are a device that's the same. And then when we put this into production, for any user, we will map their device string to whichever vector has this as non-zero. And then if we see another device string for that user that is not part of this non-zero in this vector, that is potential fraud and worth flagging. So how do we know this works? So first thing, we have some string patterns. You should always start with the simple stuff, and we did. So for instance, we know that pluses are URL encodings of spaces. So if we do that replacement and then try to check our data, we know that Google plus pixel should be the same as Google pixel. And this matrix technique, when we don't do that as pre-processing first, will reproduce the results. It also tells us things like HMD global is Nokia, which you can't really get from any string. Huawei is honor, and a few things of that nature, which once I Googled them, it turns out they're just different words for the same manufacturer. And then also, as you would expect, users with multiple devices are actually pretty rare, which was kind of an implicit assumption that this model reproduces. So this is a reasonable security feature. It's hard for scammers to exploit because the only places they could exploit are devices that are rare, and you have to find a user with a rare device in order to exploit them, which dramatically reduces the pool of users you might want to attack. And also, keep in mind, a lot of our attacks are some guy on WhatsApp who took our logo, made it his WhatsApp profile picture, and he's like, hey, sir, I'm from Simple Support. In order to avoid adversely affecting your credit, I'm going to send you an OTP. Please give it back to me. And then the user doesn't notice. Here's your OTP. Do not share it with anyone. They ignore that second bit. And then they're like, hey, who made this purchase? So it's very rare. So there are now the pool of users who could be attacked this way is dramatically reduced. And this guy on WhatsApp suddenly has to know you have a rare phone to even get away with this. So ultimately, this is a reasonable way to do it. Another use case here is the following. In principle, you could imagine doing some string matching, maybe some dictionaries to match up these devices. What if the data were hashed to preserve customer privacy? In that case, we will have no way at all to do a string matching because we only have a hash of a Google plus pixel. We also have a hash of a Google space pixel. We couldn't do string matching on the hashes anymore, but a technique like this will still work. These are sort of examples where data is messed up because of our pipeline. In principle, if we devoted enough engineering efforts to fixing them, then it could be resolved. But now let's move on to places where your data is messed up, and there's nothing even the best engineer in the world, the best team could do anything about it. Let's talk about delayed reactions. So this is a fairly pervasive problem. If I send an email today, I'm interested in its conversion rate, the number of people who open the email, click a link in the email, and then ideally later on make a purchase on some website, use a coupon code, something of that nature. So I sent this email out just now. I checked my stats, and in the past 12 seconds, nobody read it. Should I assume that my subject line sucks? It would be a little unreasonable because how many of you just checked your email in the past 12 seconds? Probably not a lot. On the other hand, 30, 40 days later, if nobody read it, pretty much nobody ever will. This is a delayed reaction problem. If I measure too early, I get a biased measurement of whether an event will occur. And if I measure late, I'm usually a day late and $1 short. Because a lot of times you have to take action more recently. So this is really pervasive. Like it's simple. We issue credit. The data we're interested in is 30 days delinquent, usually. That's like a great metric that more or less tracks our business. And it takes us 30 days to discover that. So in May, I ran an A/B test, gathered some data, tried to learn something, and on July 10th is when I actually had the 30-day delinquency data I needed to measure it. Similarly, when you're trading stocks, you buy it, you have to wait to see if it went up or down, and you might have to make decisions in the meantime. So here's a really concrete example. You want to measure a conversion rate. And I go back to conversion rates because the actual math problem, the actual predictive problem at the end of the day is really simple. The hard part is dealing with the dirty data. The model at the end of the day is easy. So here's a simple way to solve this with Bayesian statistics. Without delay, if you have a conversion rate gamma, The probability of gamma given a conversion via Bayes' rule is you take your prior and you multiply it by gamma. If a conversion did not occur, instead of multiplying your prior by gamma, you multiply it by 1 minus gamma. And so if you had n visits and k conversions, you could do recursion, and you would basically take whatever your prior is. Typically, it'll just be a flat function 1 on the interval 0 to 1, and you multiply it by gamma to the k, 1 minus gamma to the n minus k. And if you do this, what you're getting is an estimate of your conversion rate. In this case, it's about 0.15% with a margin of error that comes out very clearly from the posterior distribution. So this works great if there's no delays. But if you do this 20 seconds after sending an email, is not telling you much. So what we want to do is we now have to add time into our modeling process and model how many people would have checked their email, would have read this email, if they ever are going to. So our data set now, instead of just being a count of emails sent, a count of conversions, is a set of times. The time between the first email that was sent, the second email that was sent, and the present. And it's also the time between when they were actually opened or clicked or whatever a conversion event is. So this is sort of what I was describing before, is that if you wait a very long time, you have great information. If you wait a short time, you have bad information. And what do we do in between is the question. So the solution to this problem is something called the survival model, and there was a talk about this earlier today. I hope at least some of you attended. I'm not going to go into how to find this, but the output of the survival model is a function, R, which describes, assuming this event will be observed, what's the probability it's observed before a certain time t? I think in that talk, they actually called it S of t, and it was the probability of observing it after, but this would just be 1 minus that. So a survival curve would look like this. After, I think according to this, 8, there's like a 95% chance it's going to be observed. After a time 2 days, it'll be about 0.4. So if we go through the same process we did before, doing Bayesian stats, we discover that the probability of a click before time t, given a conversion rate, is, instead of just being the true conversion rate, it's the true conversion rate times the probability of the click being observed before t. And same thing with no click. You just have to multiply the conversion rate by that survival curve. If you do the same recursion, you get a slightly more complicated function that is still not that hard to implement in Python. And so if you use that function, you can actually get an unbiased, albeit more uncertain, estimate of the conversion rate. So in this example here, the green line, so this is simulated data. I had true conversion rate of 25%. The green line, the green curve, which is fairly narrow, is if I don't correct for delay bias, and I just use the simple Bayesian formula to estimate my conversion rate. And that's way off. If I use the survival curve to correct for the bias, what I can do here is I can get a correct estimate, albeit with more uncertainty. And as we wait longer, of course, the estimates converge to each other. So this is the same simulation run, but with more time between, let's say, send the email and measure the conversion rate. So the key point here is that in the data we have, it's an imperfect reflection of what the final email will be. There's 2 important factors: how good the email is and how much time has passed. And if we ignore the way our data is generated, which involves time, we're not going to have the most accurate estimates of it. But by incorporating time, we can actually correct things. So I'm going to close this talk with kind of an open problem that I'm constantly thinking about and never have a good solution for. The only solution I have involves spending a lot of money. So you want to build a selection algorithm. And the training data comes from the people or ads or whatever you've selected. So you want to estimate the conversion rate of an advertisement. The data you have about click-through rates comes from the ads you display. It does not come from the ads you do not display. When we issue loans, we get performance data for the people we lend money to. We get no performance data from the people we reject. Same thing happens in education. If you reject a student, you don't know how he would have performed. So this is sort of a really simple model. We have some regressor and we have performance. So you can think of the x-axis as being like a credit score, and you have the y-axis being fraction of people who repay. Now we've trained this model, which is the black line, that diagonal, and it seems pretty accurate. So we only want to approve the good people, which are the red folks up here. So we restrict those, since we are interested in loan performance, we will only issue loans to the people in the red, and we get high performance. And this goes great. Then we retrain our model, and we get a new curve. And suddenly this says that higher credit score is worse. That's not a thing I want to put into production, but this is a thing that will happen if you're not careful. We've actually, just by chopping off our data, we've turned a positive correlation into a negative one. And every so often on Twitter and the news, you discover some study coming out that discovers something weird and counterintuitive. Did you know that height is irrelevant to the performance of basketball players? Turns out in the American NBA, people who are 6 feet tall, people who are 7 feet tall, equally good. No correlation. Now you'll notice that there's basically no one in the NBA who's below 6 feet, but usually when this is being reported, no one mentions. This is exactly the selection bias. What's happened here is that there are really tall people who are maybe not as athletic, so they get into the NBA because height helps. There's also, on the flip side, there's really athletic people who are not quite as tall, but they jump higher. So both of these folks get into the NBA, and the correlation reverses itself. This was a recent one that went out about a year ago. Everybody loved it. It said that GRE is useless in predicting the success of people who get into grad school. And then a whole bunch of editorials were written suggesting, let's stop using the GRE for grad school. It doesn't work. Now, it turns out that basically no one with a really bad GRE actually gets in, and therefore they're excluded from the data when they are the generators of the correlation. So this thing happens almost everywhere. It was first known in econometrics. Heckman received a Nobel Prize for this. George Borjas, I think, was one of the first people to actually do anything with this. And there's something called the Heckman correction, which lets you mitigate this issue for linear regression, which is what econometrics almost exclusively does. It's a fantastic methodology. Here's an open problem I would love it if anyone has ideas on. How do you do this in gradient boosting machines? That's what I use, so I would be most interested there. But even how would you use this in a neural network? What Heckman did is almost exclusively based on linear algebra and normal distributions. It can't directly translate, but how can we solve this problem? The way I solve this problem is when I issue loans to a bunch of people I know are not going to pay, just so that I get their training data. This, as you might expect, costs my company a bunch of money. We have to do it because we have no better way forward. But if we could solve this problem, it would be valuable to everyone in the world. So if you have some ideas on this, come find me at the Simple booth. I would love to make progress on this. Anyway, that's where I'll leave it. I'll just say that, yeah, all of our data sucks, and we just need to learn to deal with it.
Okay. Okay. Thank you, Chris. So we're going to have both Chris and Peter. Can we have Peter also back now? We're going to have a joint Q&A with them. If those who have questions.
You have one.
Yeah?